Welcome to our wacky winter school, our wacky winter school. My name is Melissa Hart and I am the Graduate Director in both centres. We can have that discussion later. And if I have not yet met you, I look forward to meeting you in person this week and chatting. Here comes more people. As I welcome you here to the Monash campus, I wish to acknowledge that we're on the land of the Kulin Nations and pay my respects to the land we're gathered on today and to elders past and present. I'd also like to say Eid Mubarak for those who are celebrating. So it's currently sort of the end of Eid al-Adha, and to celebrate we have delicious food coming tonight. Delicious food, I've seen the menu. There's also a religious centre on campus with a prayer room for those who would like to make use. So just look up campus map and you'll find that. I'm going to give you a very brief introduction and then we're going to start our week. So these winter schools, we've been running them across, this is now across 3 centres because we're co-badged this week between the ARC Centre of Excellence for Climate Extremes and the ARC Centre for 21st Weather. So, oh my gosh, I'm not used to saying that, am I? 21st Century Weather, but 21st Century Weather, ARC Centre of Excellence for 21st Century Weather. You can tell I've been saying the other one for 6 years and this one only since February. So we've been running these winter schools now for, this is the 13th year that we've run a winter school. And what we do is we change the theme each year, we change the location each year across our 5 universities within the Centres of Excellence. The themes, they tend to range from sometimes quite a focused theme to other times a more broad theme. This year I'd say we're a bit of a broad theme, and what we're trying to do is capture what was part of the science within the WACI program, Weather and Climate Interactions program within CLEX, and then as we transition now into an entire centre on 21st century weather, which makes our wacky winter school. And the idea around these winter schools is that you're going to all graduate knowing so much about your one little part of the climate system. But in all honesty, no matter what field you go into, which sector you work with, you're going to need to understand the broader system. And so you're going to need that breadth of knowledge. And that's what we offer you through the winter school, breadth of knowledge across climate and weather. And we also allow you some collaboration activities through lab activities in the afternoon. Sometimes we throw in some professional development. You get to meet with all of our lecturers throughout the week, and we bring in our partners as well. So let me show you what this week looks like. So I'll bring this up every morning because there's a lot, but just to sort of talk through that the mornings are going to start in this room here. Actually, no, they're not. The mornings are going to start back over in Rainforest Walk to grab some breakfast. Then we're going to come over here at 9 o'clock and start with some science lectures. Starting from tomorrow, we're going to have a forecast update every morning from Michael Barnes. So really interested, hoping for a really interesting weather week. And then we're going to have science lectures in here. We'll have a stretch break between lectures, morning teas, we'll go back over to the other building. So we're going back and forth, getting a little bit of walking in. We'll have lunch over there. Afternoons, we're going to have interactive labs. So for the first 3 days, we'll have a chart discussion activity and you'll be working in groups. Those groups are on your name tags and you've purposely been put into groups with people working in different areas, different universities, etc., etc. So at morning tea, look for people who have the same group as you. Then we have another lab on Thursday about spectral filtering, and I sent you all an email last night around just ensuring you have an NCI account. So follow up on that before Thursday. Then on Friday's Bureau Day. So as I said, we often include our partners in our winter school. So usually I invite partners to come and lecture. But this year I was like, we're in Melbourne, let's go to the Bureau. Rather than them coming to us, let's go to them. So I'm super excited. We've got a whole lot of talks. We're hearing actually directly from the forecasters, and we have some tours as well of the Bureau head office. So we can talk a little bit more about Friday closer to Friday. So, but for today, long day. At the end of the day, we're going to have an icebreaker activity back in the building we were at this morning with delicious food. Actually, before I introduce our first speaker, I'm going to look at my notes and make sure I haven't forgotten anything I'm supposed to tell you. All the notes that I wrote on the plane yesterday. Before I introduce our first speaker, I'm going to introduce Angela. I know Angela's like, what? I was going to give you the opportunity to introduce your team who are going to be here this week. So Angela Kaplish is the CLEX knowledge broker, and she has members of her team here this week. Did you want to say something, or do you want me? Yeah, okay. You looked really scared then. I thought, we had this conversation.
It's got last night, so... Okay, hello. I'm Angela, and I'm from one of these centres, wherever the logo's gone. I'm from CLEX, and I'm one of the knowledge brokers for CLEX. And I'm going to tell you a bit about the impact and engagement that we do at CLEX, but also will extend to 21st century weather as well. So I'm going to introduce my team as well, one of whom is here. So this is Alice. So there's two groups that make up impacting and engagement, which is sort of a bit arbitrary, but it's sort of knowledge broking and comms. So we work together. We're one big happy family. And I'm Angela Kaplish. I'm based at ANU in Canberra. I'm a former public servant with federal government, and my job is primarily to get CLEX and all your research in front of public servants, senators, MPs, which we've done over the sort of past couple of years. So that's getting your papers that you produce, your information, as well as just basic climate information in front of them, educating them and telling them how that can shape their policy going forward. Alice is also a knowledge broker based at Monash, and she does the nuts and bolts of all of that. So she sort of does submissions to public inquiries about climate, as well as doing some of the explainers. I think she's worked with many of you on topics like El Nino and coral bleaching, for example. And then the other members of the team are Georgie Harmer. She's a graphic designer. So graphic design is used to enhance and make the scientific information that you're producing a bit more accessible. So she's probably helped some of you on infographics for your papers, but she's also been sort of responsible for developing and extended the brand of CLEX. And when I say brand, it's sort of more to give CLEX a sort of much more professional and reputable face in front of all the people that I will put the products in front of. And then we also have a comms element, which is all about promotion. So it's promoting your papers, promoting you as climate scientists, and promoting CLEX. So that's done by Victoria and by Law, who some of you know. So Victoria and Law are both based at UNSW. So all that work sort of comes together. I think maybe some of you know about this. This is the State of Weather and Climate Extremes report, which we produce. So all that work comes together in producing this document. Many of you have contributed to this, and going forward there'll be some sort of similar document, perhaps with the next centre as well. So that's our team. We'll be around all week, so if you've got any questions or anything you'd like to ask, or any promotions that you'd like us to do, or interesting science that you'd like to promote, come and talk to us.
Thank you, Angela.
Thank you.
One last slide from me. This will take you to the Winter School website. We will update this continuously throughout the week as people send me slides, as people send me any documents you may need for the labs, and beyond as well. So we're recording everything we're saying here, so we'll be careful what we say. And eventually we'll put the recordings up as well, so if you want to revisit or for future students. So keep an eye on the website. That is me done. I get to now unplug this and introduce our first speaker, who is Christian Jakob. Christian is the director of our brand new sparkly Centre of Excellence for Weather of the 21st Century, 21st Century Weather. Oh my gosh, why is this up? 21st Century Weather. Maybe we do, in addition to a logo, we need...
We are looking for a jingle if anybody's...
Yeah, I think we do need a jingle.
This week, any of you want to get their creative juices flowing? Yeah. Go for it. Send it in.
So Christian's going to set the scene as to why we are going to spend an entire week and then an entire 7 years on weather and climate interactions and why we're interested in weather science. And I will hand you over to Christian.
All righty. Let me turn this on.
Can you hear me? Can you hear me through the spooky speakers in the various places in this room? I'm sorry for that. Welcome everybody to Monash. And Melissa said she was hoping for interesting weather, so the weather chart. The weather's always interesting. Melissa, please. It doesn't matter what it is. Something not happening in the weather is just as interesting as something happening. And actually, the last 3 to 4 weeks here in Melbourne, for those of you who live here, you would have noticed, directly relate to some of the research we want to do in this new Centre of Excellence. Do we have a pointer? We probably don't. I messed up. I messed up on pointers, I have to say. So, because it hasn't been very windy, and it not being windy may not excite us as climate scientists, but as I will demonstrate over the next 45 minutes or so, it should excite us as we're moving forward in our economic plans and in our plans to mitigate climate change. All right, so what I'm going to do is I thought long and hard. Oh, and I did not write my talk at 8 o'clock at night, and I did not write it on the plane. I wrote it last week in peace and quiet, and I'm telling you this because I don't want you to think that life of a scientist means you have to work at 8 o'clock at night on a Sunday. Because if you're organized and you plan ahead and you think ahead... Oh, yeah, come on. You can do it the week before, and you can have a weekend that's very relaxing as well. And I did, I claim. Actually, it wasn't terribly relaxing because my back hurt, but that's a different story. Which one is the...
Oh. Did I turn it on?
Well, the back and forth, I don't care. Is there a laser pointer on this?
There should be.
Okay.
Yeah?
Yeah.
That little middle one?
You sure is the battery in there?
Okay, is it
Did we
turned
switch
on?
it on?
I don't know.
No, we didn't switch it on. Well, that explains a lot, doesn't it? So this works, and now I have to find where the... got it. Thank you. Thank you, Melissa. I can only point at one, so that'll keep you entertained. I'll switch, and you have to figure out which one I'm pointing at. So there's really two purposes to this talk. One is I've taken a lot of the slides that I presented to the panel that reviewed this center and actually approved the funding for it in the end. So that's about motivating why one may want to think about the weather as the climate's changing, right? So this is what the center is about, is that climate's changing and with it the weather will change, and actually there's a lot to be learned still about how the weather will change as the climate's changing. So I'm going to motivate this, and you can actually be the review panel at the end of the talk, and you can say, oh, God, why did they give so much money to this nonsense? Or, this is really exciting, I want to be part of it. I'm hoping it's the latter, but I can't guarantee it, right? I will try my best to make it the latter. And then I've thrown in, which I didn't do for the review panel because one doesn't do that, I've thrown in a bit of science to really get some examples for you as to how we might approach some of these problems or where we are, what's the status quo, and why, is there so much more work to do. All right, shall we get cracking? All right, so these centers, in case you didn't know, you're asking for $35 million for 7 years. 5 million a year, and then you get a bit of extra from the universities, but that's what the ARC, the Australian Research Council, will give you. So see whether you think I'm making a convincing argument for $35 million, which is actually a lot of money, as you might imagine. And you are here because the previous center, CLEX, got about $35 million to do what it does. So to get $35 million, you cannot make small-scale arguments, so you have to have some bold statements. So let's make the first bold statement. Weather, in CLEX, weather is a hazard. It's an extreme, kills people, it does terrible things. The first bold statement we make, weather is so much more than that. First and foremost, every day, weather is a resource for both us as humans and for nature. And if you need sort of some sectors for which you want to think about that to be true, just take agriculture. Agriculture relies on water, fresh water. Where's the fresh water coming from? The sky. How does it get into the sky, come out of the sky? Weather. Not climate, weather. I'll convince you of that in this talk. Renewable energy, poster child for weather. The fuel to make electricity is not climate, the weather, right? It's the weather that's making every day, every hour, making renewable energy. We'll come back to that. Fresh water, I've already mentioned, we drink it. We don't just put it on plants, we drink it as well, so we need it. We tend to go where the weather's nice. That has something to do with climate, of course, as well, because in certain regions of the climate background sets what the weather we expect in this region would be. And of course, ecosystems thrive on water, sunshine, so on and so forth. So they rely on the weather. So bold statement number one, don't think of the weather just as a threat, which it also can be, of course, and we'll come back to that. But most of the time, most of places on Earth, it's not a threat, it's a resource. But even when it's not a threat, we use it. We use it every day. It's just so common to us, we've stopped thinking about it. But we do it. Second bold statement, climate change will make us more weather dependent. Well, let's try and back that up a little. Why am I saying this? I'm saying it because of this bit in the middle. So our climate's changing, we know that. And we've decided, we know what to do, right? We know how many more gigatons of carbon we can put in the atmosphere. And we know that that's not a lot. So we now need to change the way we live so that we don't emit carbon. And one of the big mitigation strategies in every country in the world is to deploy renewable energy. Right? Because that doesn't emit carbon as it produces electricity. And we want to do this, we want to get to net zero emissions by 2050. Electricity alone won't get us there, but it is a bit of a poster child for it, right? And I picked two pictures where this can go terribly wrong. This is the Ararat wind farm in Victoria on a day where it's foggy. What do you know about foggy days, people? What do you know about the weather? How much wind do we have on foggy days? None. Yeah, very little, close to none. Because if it's windy, the turbulence get going, and the turbulence would mix out the fog. And kind of turbulence, kind of wind. And I've also found a picture of a big solar installation in Western Australia on a cloudy day. So winds and cloud are suddenly things that we care about, and we always cared about them, but clouds we cared about for climate sensitivity and big questions like that. Now suddenly we have to care about clouds at the level of what's going to happen to clouds as the climate's changing, and how might that affect our production of solar power? What's going to happen to wind as the climate's changing? It's a very difficult question. How much have you read about it? Not much. It's not much there. There's some, but not all that much. Okay, so what do we know? Next argument is, so we know a lot about climate change, right? These are pictures you've seen a million times. These ones are from the IPCC report. We know the Earth is going to get warmer. We know how much warmer depends first and foremost not on uncertainties in the science, but on uncertainties in human behavior. That's indicated by these lines, right? These are the different economic scenarios of what we do, how we behave, and they lead to very different outcomes. For each outcome, there's uncertainty, but the signal as to how bad it's going to be is clearly determined by our behavior, right? So that's just worth pointing out every now and then. It's not uncertainty in the science. It's for global mean temperature. There is uncertainty, obviously, but the first order determinant of what's going to happen are humans and how they behave. We also know extremes are getting more extreme. But there's an interesting one. Extremes are getting more extreme. So that statement every card-carrying climate scientist would sign. Now, where and when and by how much, you'd probably start an argument amongst most climate scientists. Because we don't know that well. It's a bit like your GP, and mine says this a lot these days. GP tells you, Christian, you're getting older, you're going to have some health issues. And it's true, because as we get older, we have health issues. But what I would like to know is when, which ones, what exactly could I do in preparing for them, right? Could I take some pill now so that I don't have this particular issue? But my doctor can't do that. Just like in climate change, we can make a general prescription. The doctor would say, exercise, don't smoke, don't drink too much, all these things, and take your blood pressure pills if you have high blood pressure, so on and so forth. But none of them target anything specifically, but they help in general. And we know that for climate change. Don't emit so much carbon dioxide, right? But so the general things we know, but we don't know the details. So really knowing the details, where, when, and by how much extremes get more extreme is important, because it feeds directly into our plans. What we really would like to know, what people on the ground, people who plan, make decisions, but even you and I would like to know, so the communities, governments, businesses, is how are these weather resources and hazards that the weather also brings with it, how are they going to change? And how are they going to change? Actually pretty soon, they want to know, which is probably the hardest thing to know much about. And these are determined by weather systems, as we'll come back to. So what we'd really like to know is, how do the weather systems change? And that's where we come in. So to build this bridge between what we do know on relatively large scales and what we need to know on relatively small scales, and to actually understand why it's happening. As a famous quote that I didn't put on here because I didn't want to push the panel too far. It's very old. It's by the Greek philosopher Plato. And Plato said, a good decision is based on knowledge and not on numbers. Digest that a little. We are extremely good at producing numbers in climate science and in weather prediction. We have models, we run them into the future, we have heaps and heaps of numbers coming out of them. But the knowledge that underpins these numbers is way more limited than the amount of numbers that we have. And this is what the Center of Excellence is about, to build the knowledge that bridges between the larger scales and what happens on the ground. Okay. Why is this so difficult? Well, that's the next thing you need to convince people of, right? So I've made the case, I'm motivated, we want to know about weather, but it better be difficult, because why would I give you that much money if it wasn't difficult, right? So centers of excellence are meant to look at difficult things, not just stuff that you can do on the back of an envelope on a plane. So why is it difficult? Well, this is a very common figure, right? Many of you would have seen this. It's just the climatology of rain on Earth. And for you, I can go over this very quickly. It rains a lot at the equator or near the equator in the tropics. Then there's a region where it doesn't rain very much at all in the subtropics, which Australia sits smack bang in the middle of, in case you hadn't noticed yet. And then there's this region we call the exotropics, where there is a maximum of rain again. It's mostly over the ocean, even in the northern hemisphere, but it also creeps into the land, right? So this is the rainfall climatology on Earth. And then when we talk about climate change, I need to sit down for my back here. When we talk about climate change, people say, oh, all right, climate change is this picture. We want to know, how is this picture changing as the climate is changing, right? Okay, that's a fair question. And then you go to the IPCC report, and there's 2-degree warming, 4-degree warming. You see all these pictures, which I deliberately didn't put here. Now, here's a little shock for you. This is also rainfall every half hour from satellites, and it's a movie, obviously. It's a loop. And this is how the rain actually falls. So this picture we just saw is an average of that. So to know how that average picture changed, well, let's have a look first. So what do we see? So in the tropical regions where we saw these bands, you occasionally see bands, but most of the time all I see is blobs. Most of them move from the east to the west, because that's the prevailing wind direction in the tropics. Some of them move from west to east, because there are other circulations going on. They're blobby, some of them live long, some of them don't live very long, and they're preferred regions, and those preferred regions average out into those bands, which are the intertropical convergence zone. But the rain doesn't fall steadily in a band. which is this false impression we get from this climatological picture. Then there's a region where it doesn't rain, that's confirmed by this. But then in the extratropical regions, the structure of the rain is very different. It's band-like. Of course, these are fronts. We call them fronts in meteorology. They're somewhat equidistant, or not equidistant, but they have a certain distance. I'll play this again, just for fun. So they have a certain distance in which they occur. They occur regularly. They seem to be more, over the ocean, but not. This is in May 2014. Doesn't really matter, but May matters because it sets the season in which this movie was taken. So if you really want to know how this first picture is going to change, the question isn't how is this first picture changing, it's how is this changing? Because that changing this will change that picture. It's not the other way around. It's not the average will change and then something will happen to the weather. No, something will happen to the weather and that will change the average. It's just as good an argument. So there you are. That's the question we need to answer. Another reason it's so hard is the weather. You saw this, these little blobs in the tropics, acts on scales that many of our climate models that we are using day to day do not have much knowledge of because the resolution of these models is too coarse. And here's a very simple example that I like to use, mostly for non-scientists. So for you, I could have used the more sophisticated example. But this is the Access Climate Model as it was submitted to and used in the IPCC 6th Assessment Report. This is the orography of Australia in that model. Yeah, that's our state-of-the-art global climate model. Okay, what do you know about the orography of Australia? So in this model, the highest mountains are in central Western Australia. Is that true? Not really, is it? There's good news in this model, though, because actually if you want to go from Hobart to Melbourne, you don't need to take a plane. You can actually take the car. You can drive up to Melbourne. That's kind of nice. Actually, in the end, that's not true. There is actually an ocean point between Tasmania and the mainland in the model because they use this elevation and then they put on a land-sea mask where they say what's the percentage of the land that has this orography. And it's very small here, so they make this an ocean point. But it's still fun to say it, right? And it's a bit like taking some people here and pixelating them. And you don't know who they are, but now you do. And this is the elevation above sea level at 5 kilometer pixel size. And of course, you'd think it matters. And keep it in mind, I will show you an example where it matters a lot when we look at a few science examples, right? Here is where the highest mountains are. And the reason this comes out as the highest mountains in Australia in a low resolution model is simply because they're horizontally extensive, not vertically necessarily. So that's an issue. Okay, so how are we going to address this issue in this new center? Well, we've made ourselves three major themes of research in which we want to work and will work. The first one we call circulation change, and it really wants to ask the question, climate change, climate variability, and weather systems are all connected to each other, as I tried to explain in the motivation part of the talk. So how are these going to change? So for this to work, we need to learn more about weather systems. What are they? What are their characteristics? What are their dynamics? What are their thermodynamic processes? How do they link to things will come later? But purely about the actual thing that is the weather system. And a simple example of a weather system, if you want, is a low-pressure system or a high-pressure system. But once, and as you will learn this week, there's actually way more insightful and deep ways to think about weather systems once we think about the dynamics of the atmosphere, right? But high and low pressure systems, fronts, cool changes, these are good examples for weather systems. How does climate variability change weather systems is a question we actually know relatively little about, as I will show you. We know the statistical relationship of climate variability to rainfall, say, but rainfall isn't a weather system. Rainfall is just an output of a weather system, if you wish. So the mechanisms, we know much less about the mechanisms than we know about the statistics, numbers versus knowledge. And then climate change, of course, will affect weather systems, but climate change will also affect climate variability, and the climate variability already affects climate change as well. So this is a nice circular field of work that we want to be in our new center. Okay, and now I want to do a bit of science and give you a few examples of where we don't know and do know things, or where we realize knowing more would be a good idea. So here's the poster child example in Australia. This is from the Bureau of Meteorology, and it shows the winter and spring mean rainfall expressed in deciles. So it asks the question, which part of the PDF is the rainfall when we're in an El Nino year? So they've taken 14 El Nino years here, and they say, what's the rainfall in Australia, in which decile is it? And this very famous relationship comes out that most of eastern Australia, the eastern half of Australia, tends to be in the lowest decile. And we like to show this, and then we are happy, and then we forget to see some real subtleties, and we'll come back to them. We see that on the south coast, and particularly the east coast, Sydney, right, is actually not true at all. And then we get shocked when we get wet in Sydney during an El Nino, right? But it's not true. I mean, if you look carefully, we all see this big red blob, and they say, yeah, Australia's going to be dry. El Nino, we're going to be dry. So Serafin Hauser, and she was a student from Germany who came to Monash for a period for an exchange, and she worked with a group here, Michael Reeder and others. And the first thing she did is say, well, let's take this picture and be a bit more dig a bit deeper, and she found that the rainfall behavior actually falls into 4 categories. She used cluster analysis. Details don't matter too much. You can do it with machine learning if you want. And she found that actually there's 4 types of rainfall patterns when we are in an El Nino. There's a wet everywhere, which really would shock us, right? We would never assume that could happen, but it's rare. It only happens 8% of the time. But that's still 1 in 10 El Ninos, right? Sort of 1 in 10 El Ninos can be wet everywhere. Then the dry everywhere is the most common, happens half the time, roughly. And then sort of the other 40% are spread between 2, where it's either wet in the east and dry in the south, or dry in the east and wet in the south. Right? So we already see the story is more subtle, but then the weather comes into her study. She then looks at weather systems, and I can't possibly show the entire study, I just want to give you examples. And her weather systems are things like cutoff lows, cyclones, blocking anticyclones, extensive moisture transport, and then these WCB things stand for warm conveyor belts. They're part of low pressure and frontal systems. And this shows which of these systems occur less in the dry everywhere state, which is the most common state. Well, and you can see the entire eastern half of Australia has less of almost every weather system imaginable that you might think contributes to rainfall, right? They're just gone. They're just not there. Interesting question, why? What are the mechanisms that push them around? And then when it's wet in the east and dry in the south, what do we get more of is what this figure shows. And we get more blocking anticyclones to the south, and we get more cutoff lows right here on the east coast, on sort of east and southeastern half. And we know cutoff lows are associated with rainfall. So there's a bit of insight, first insight emerging from studies like that, is how weather systems interact with El Nino. And it raises our awareness that actually that rain coming or not coming depends on weather systems being there or not being there, and not just on some sort of mean climate state change. Okay, the next example, oops, how do I go back? Oh, now I went back too far. The next example is more recent work from Tess Parker and Ailey Gallant, also done in CLEX, and there we're looking at drought. And one of the interesting things they found, and these are figures of the relative change in days that lead to the onset of drought, right? What rainfall values do we actually see decreasing and contributing to this onset of drought? And the bottom line, and it's very hard to see and it's a bit messy, is that really the light rainfall days decrease, but not all that much. What decreases the most around drought is the heavy rainfall days, right? So that's the first thing. So the relative decrease in the relatively rare but important heavy rainfall events is the largest. So it's the heavy rainfall events not being there that contributes to the onset of drought. And then if you look at the contribution that makes to the accumulated rainfall, you also see the larger contributions come from these larger rainfall amounts. So it's a few days Actually, it's relatively few days. This is in percent relative to their occurrence, so it looks like 80%, but we're talking about a couple of weeks. A couple of weeks of rain being there or not being there makes a big difference to whether Australia is going to go into drought. They also showed that coming out of drought works in a similar way. It's a few days, few weeks of rainfall. So again, it highlights the importance of weather systems in going into something that we think of as climate, as in going into and out of drought. Okay, the second theme, so that's the circulation theme in some examples. The second theme we want to work on is then what we call weather change, and this is really, what really people care about is not weather systems. They don't care about fronts and highs and lows. What they care about, what's the wind, what's the temperature, what's the rainfall, these are the questions. These are the things, and they really only care about them on the ground. If you didn't already know, you will know at the end of this week. The weather doesn't happen on the ground. The weather happens in the lowest 10, 12, 15 kilometers of the atmosphere, and the air 5 kilometers above us actually influences what happens on the ground, right? So you knew that. Well, many people don't know that. So this theme is really about how do weather systems translate into what we call, and we pick two areas, weather resources and high impact events. And you can see a subtle difference here, and you may not think it's a big deal. So weather resources has become a big deal because it turns out, interestingly, not many people think about the problems that we should be working on in this context. I've been giving this talk in various locations around the world these days, and they all say, oh yeah, I haven't thought about weather as a resource. But it's increasingly going to be a resource, right? I mean, the entire electricity grid will be weather-fueled in 20 years, 30 years, right? That's remarkable. It's a remarkable change. In fact, it's a change that I still don't think we've grasped what we've done, because our entire history as humans was to be less and less weather dependent. We built shelter, we built irrigation, we built air conditioning, we built heating. All these developments, all the engineering we did was to be less weather dependent. And with this change to net zero and renewable energy, we've become incredibly weather dependent. I don't think we've digested that yet as a species. I don't think we are quite there yet in, having grasped what we've just done. So we're making ourselves extremely dependent on the weather. And we've changed extremes to high impact events. And both these names are important. Language is actually incredibly important. The words you pick are incredibly important when you think about problems, because they change the way you think about them, I think. And why are they important? Because none of this is defined by climate scientists. Climate scientist doesn't define what a resource is. Climate scientist doesn't define what high impact is. It's people who use information, who make decisions, who say, oh, for me the resource is this, and I need to know more about that. So as you'll see later, one of the goals of our new center is to work very closely with government and industry to actually help us work on the right things. This is how, it's the simplest way to phrase it, right? If we picked, and there's a nice example in high impact events, which is the opposite of this. This was a big windstorm in South Australia, and we recently had one in Victoria, so I could have shown you photos from Victoria around big thunderstorms with strong microbursts and strong wind gusts. But I give it the poster child for a high impact event that climate scientists, there's evidence, have not cared about is no wind. No wind is not something a climate scientist is it's pretty boring, isn't it? Right? I mean, no one dies, no one gets hurt, no one, and it's kind of so no one studied it. In 2050, no wind will kill people. No wind over a long period of time, over a large area, will stop the turbines from spinning, will stop the electricity from coming, and if we didn't plan for it and didn't think about it, the air conditioning will go off in a heat wave, and people will die. So there's a high impact event that we as climate scientists would sort of not come up with ourselves, and it's driven by our reliance on renewable energy in 30 years. that makes it a high impact event. So we better start studying it now, right? So we're not surprised when it happens and that we know a little bit more about it. I want to give you an example that's more about the resource. This is a paper a colleague of mine here at Monash did, Andrew Gunn. I'm co-author, so we worked on this. And we were looking in Australia at something people didn't seem to have looked at very much. And we were asking what's the role of climate variability in the wind resource in a very simple way. But the first thing Andrew did, which was really cool, he said, well, really, if we want to distribute wind farms optimally, let's before we look at resources, let's distribute the wind farms optimally. Let's not worry about where they can actually go. Let's just ask the meteorology where they should go, right? And they should go, of course, in places where the wind is not correlated with each other. So you want, if it's not windy over here, you want it to be windy over there, so that for your grid, you're still producing a certain amount of power, right? And if you do some fancy mathematics on this problem, this is what you get if you allow it to be anywhere in Australia, right? So this is a map of the least correlated patches of land in Australia. So there they are. It's great. So what he also plotted is the grid. So these lines are where the power grid is at the moment, and the dots is where our wind farms are right now. And there is, so that's the AEMO grid, the lines, and these are the existing wind farms, right? So the first thing you see is they're mostly in places where they're correlated with each other, right? So that's not good news. Of course, you can zoom in a little bit more, but hey. And then you can also see that all this is, this sort of talk about infinite renewable resources is kind of nice if you believe that you can build a power line from here to there, or from here to there. We do have infinite resources, but not all of them are accessible. It's a bit like people say we have infinite oil, but some of it is just not accessible, right? It's just a stupid thing to say, I think. So we have lots of renewable resources, and we need to be smart in exploiting them. Okay, so then Andrew made sort of a few hypothetical models. One is the boilerplate one. You can have it anywhere in Australia. But then he also calculated, well, what would it look like if it had to be within 100 kilometers of the existing grid, for example, and what is already there and what's being planned. And one of the things we found out, it almost doesn't matter. So these different colors are, this is the operational plus already planned, already approved. This is Australia-wide. This is... oh no, this is only at the AEMO grid. This is the AEMO grid connected to the Western Australian grid. Did you know we had no connection in electricity between Western Australia and the rest of the country? How are we going to build a national, sustainable, workable electricity solution when we do stuff like that is a mystery to lots of us, I think. And then this is the copper plate, the green one. But you see, the curves are not that far apart from each other. They're a little bit apart from each other. And what this is, so instead of thinking about wind, we're thinking about how much power can we produce. Wind power is a very nonlinear function of wind. It's very nonlinear. It's sort of initially exponential, then it's flat, and then it's zero. So when the wind gets very strong, so when it gets somewhat strong, they have to throttle the turbines so they don't spin too fast. So that makes constant power for a while, and then if it gets even stronger, they have to turn them off because they can't put the brakes on hard enough. That's why it becomes very nonlinear. Incredibly important for climate science, by the way. Just a little anecdote. You can tell I like telling anecdotes. When you want to download data from CMIP models to look at your favorite thing, how often do you think we have wind available at 10 meters? Well, if you're lucky, it's 6 hourly. Now, if you have a highly nonlinear curve like that, how good will your estimate of daily wind power be if you only sample the wind every 6 hours? It's going to be terrible, actually. So even in simple technical terms, we always say we're doing what we're doing for society. We're not even saving the right stuff in our climate models if we are about society. We're doing a lot of things for science, right? But we really have to up our game a lot if we truly want to do this for society, right? There's, at all levels, from the technical to the scientific, there's a lot of work that needs to be done to get us to that level. Back to these curves, though. So this is the wind power. So it's already taken this. So we used hourly data from ERA. better than 6 hourly. Not great. Hourly is even not good enough, probably, but it's good to give you a first estimate. And this is just, we wanted to look at what's the variability in this, right? What is the variability in the wind power from year to year? So this is an annually smoothed time series of wind power. And what do we see? We see there's actually can be swings from 5% above average to 10% below average from one year to the next. And guess what? What's this year? It's 1997. Anybody remember what happened in 1997? Big El Nino. Guess what? El Nino doesn't just affect rainfall. It affects wind as well. How could that be? Well, might it affect weather systems? Oh, maybe that's what's happening. Maybe the weather systems change and everything changes. The temperature, the wind, the rainfall, and maybe our view of the world of, oh, let's look at rainfall. Oh no, I want to look at temperature is also a bit flawed. Maybe when we think about weather systems causing what we are observing, the correlations between these things should be taken into account as well. And some of you do that, of course, already. Anyway, so these swings can be very large. The bottom figure, this is why I wanted you to remember the orography, shows us the influence of the interannual variability on wind power, and where it's yellow, that influence is large. And you can see that it's very large near the orography, where there's strong variations in the wind. And here's some really bad news. This is the correlation of the Nino, which one is it, 3.4 index with wind power. And why it's bad news is because it's spatially correlated. So you might have hoped that it's only one part of Australia where it's less windy when we are in El Nino, but no, it's actually quite an extensive part, and it's actually where most of our wind assets are. We're a bit lucky in Victoria here, so there's a bit slightly positive correlation there. So again, El Nino is a big player in wind as well, we found, and this sort of, even if we make ourselves really spatially anti-correlated, some of the variability we have to deal with is correlated. We don't know anything about change yet, because we haven't looked yet, and the models that we have available to look at it are probably not up to the task. And we'll come back to that, why even downscaling won't save us in a second, or might not save us. It might, but then it might not. Okay, so the third theme then, I said that our models aren't up to scratch. So one of the things our center is saying then is we need to change that. We need to make them up to scratch. And one of the big things we would like to do is use very high resolution models in our work. And we will use them for science. So our goal is not to make new projections until 2100 using ultra-high resolution models. And I'd show you at the end of what I mean by ultra-high. So just as a flavor, a few kilometers globally would be really nice, and a few hundred meters for regional models. And that's at the end of the center, so in 7 years' time, right? So it's not, we can't do that right now because we don't have the computational power to do it. But we can start doing experiments, and here's an example. We did an experiment quite a while ago, by running this entire region here, and you can see Australia in the background there, at 400-meter horizontal resolution. I'm taking guesses. We ran it for 3 days. You can see there was a tropical cyclone. It's tropical cyclone Debbie. Was interacting with an extratropical cyclone that was going through down here. These are wind gust fields, and there's nice interactions there, and all that's all lovely. So we ran this thing for 3 days. 3 days real time, right? So forecast was 3 days long. How long did it take to run? Just for fun. 10 hours, 12 hours? Any other takers? 6 days. Any other takers?
3 days.
3 days? Weeks. Well, 9 days. And it produced 80 terabytes of output. That's scary, and again, it brings back really nice challenge. So you can see this, oh my God, is one way to react to this, right? And I do on occasions. But another one is, this means the way we do modeling has to change. This lazy attitude like, let's run another 500-year coupled, pre-industrial something at low resolution, which we can at low resolution, but let's just do another one. Let's do another 200 years. None of it will work. So we have to challenge ourselves and to say, well, what can we learn from these high resolution models, given that we cannot run 500 years coupled at high resolution? If we think high resolution matters, and we think it does, and I'll show you 2 examples in a second, then we need to be smarter. Okay, so why would you care about higher resolution? So here's one that's not about terribly high resolution. This is an example from a paper by Steve Yeager out of the NCAR group. And they looked at something that has been pointed out a few times, and that is if you look at the temperature trend, this is from 1979 to 2017, so relatively recent, and at the rainfall trend, which happens to be 81 to 2019, then the observations show this sort of warming in the western part of the Pacific and not much, it's slightly cooling in the eastern part, and the rainfall looks distinctly like an La Nina signature, right? More rainfall in the west and less rainfall in the central and eastern Pacific. If you look at the bottom, this is from a decadal prediction system that they have at NCAR, run at 1 degree resolution for the atmosphere and ocean. And this is the temperature trend, and this is the rainfall trend, and it looks distinctly like an El Niño, doesn't it? So nothing like the observations. This is also true for CMIP models. It's unclear whether this is a fatal flaw or just climate variability. It could just be decadal variability. The jury is still out there, what it is. So then they reran this entire set of decadal predictions at higher resolution. It's not terribly high. This is about 25 kilometers for the atmosphere and about 10 for the ocean, but it's much higher than 1. And lo and behold, now you see that the temperature is actually increasing more in the west than the east. It's not perfect, but it's better. And there's some hint of a La Nina-like rainfall response like we see it in the observations. So this is a big deal, right? So we don't know yet whether this will go on into the future or whether it's just a sign of climate variability in the last 40 years. But higher resolution models give an answer that's closer, and they change nothing else really. They have, of course, you always have to make a few small changes when you change the resolution, but they didn't terribly work terribly hard to make this a better model other than changing the resolution. For Australia, this is absolutely critical. Which one of those two is it? Is it El Niño or La Nina? It has such a big effect on our weather that if we don't even know which one, what's our future like? Is it more El Niño-like or La Nina-like? So really, it's a big question in front of us that we have to answer, right? The second thing is anybody working on the land? So this is a land-atmosphere coupling example. This comes from a group at the Max Planck Institute, who are a partner in CLEX, also a partner in our center. It was John Hin Lee and Kathy Honegger, got published recently. And on the left-hand side, you see a low-resolution model. Right-hand side, you see now a 5-kilometer coupled model. And what they're showing is some soil moisture index rainfall correlation. So it's how does the rainfall in the model react to high or low soil moisture locally. All right? And what you see is in the 160-kilometer standard model they submitted to the oh no, this wasn't even submitted to the IPCC, I don't think, but a standard climate model. You see this correlation is highly positive. So when the soil is wet, it rains more. And so there's a direct relationship between soil moisture evaporation and rainfall. It turns out in the observations that's not what we see, and it's hard to show from observations. But in some regions people have looked, and it's actually way too positive in these models. And just running the same model at 5 kilometers, they didn't change anything in the land model or in the atmospheric model. They just run at 5 kilometers and they turn certain parameterizations off, in particular the parameterization of deep convection, changes this picture from strongly positive to weak in general. Just to show that this isn't just a cause and effect the other way around, they also do the same correlation with the next 9 days of rainfall. No, sorry, with this, the rainfall after the soil moisture. Yeah, it's that way around. So it's not that it rains and then the soil moisture gets high, right? It's they look at soil moisture now, what happens the next 10 days or 9 days, and the picture is pretty much the same. So again, the little bit of observational evidence that there is looks more like the right-hand side than the left-hand side. So again, in our climate models, this is a big deal, people, right? If our climate models have this very strong positive correlation, that also means they have very strong positive feedback. If the soils get wetter, it starts to rain more. But if the soils get drier, drought anyone, the models stop raining when perhaps they shouldn't just yet. And there's a thought that this has to do with given what mainly changes when you go to high resolution is that it has to do with the way convective rainfall is parameterized in these models and actually behaves quite differently. This has been known from regional models for a while, that if you run regional models as high resolution, they look more like the right-hand side. But it's a big deal. And it's another reason to think about high resolution modeling in the center. Because it's a fundamental flaw, potentially a fundamental flaw in the CMIP family of models, right? Not just a little flaw, a fundamental flaw. And the reason is, of course, you can see that the low resolution model, this is evaporation against rainfall from the low resolution model, and you can see that the more you evaporate, the more you rain. It's a very simple-ish relationship. Whereas in the high resolution model, this is true for low evaporation rates, but then it is not true anymore for the higher evaporation rates. Okay, so here's our plans for the new center. So by 2026, we want to be able to run atmosphere land at 10 kilometers and ocean at 10 kilometers, and atmosphere land ocean coupled. Since you're students, can I indoctrinate you with some other thing? Coupled models. We call models coupled models when we couple an ocean to them. And we call them atmosphere only for the other. Anybody working on the land? You should get your pitchforks out if you're working on the land. And you should go on the barricades, because it's just not true. All models are coupled. Some are coupled only between the atmosphere and the land, and some are coupled between the atmosphere and the land and the ocean. Atmosphere-only models also exist, but they can only exist if they have no land surface parameterization, prescribed sea surface temperatures. For those of you who have seen aquaplanet models, those are truly uncoupled models. So let's try and change the language, shall we? And talk about coupled models all the time. And I would like to call them ALO, right? Atmosphere land or atmosphere land ocean. It's a much better way than coupled or uncoupled. But it's going to be a hard road to walk, because for 40 years, that's the lingo that has emerged. In 2028, we want to be at 5 kilometers globally. And we would like, regional models, we really want to start atmosphere land only at 1 kilometer. This is where the Bureau is at the moment with their forecasting systems. And then testing their new forecasting systems. And then we want to go to 500 meters. And we want to develop an atmosphere land ocean model, fully all spheres involved, that goes across the Indian Ocean, Pacific Ocean. So it's quite a large regional model. And that would probably run at somewhere like 3 kilometers and then 1 kilometer at the end. And at the end of the center, we also would really like to be able to do at least some kilometer scale global experimentation, right? Okay, so this is the research program, and this is largely what I'm going to talk about. I'm not going to bore you with much more. So if you put all these things together, these are simply taking my slides and putting the figures together in a sensible way. What you find is that, and this is the sort of nice point to end mostly on. I won't end here. Don't get your hopes up. You see climate change, climate variability relating to weather and resources and high impact events. And in general, in most times when we do our work, we go directly from those two to those two, using statistical methods most of the time. And what I hope I convinced you is the thing that sits in the middle is weather systems. The thing that translates this, but also changes this, and actually makes these are weather systems. So they're an absolute central part of our world. They should be an absolute central part of our thinking, which is why the new Center of Excellence puts them central to its reason to exist, right? And then models and observations are the tools that we will bring to exploring this space on how these two interact with these, create these, and vice versa. Okay, who's involved? Here's a bunch of logos. I won't tell you much, but it's the same 5 universities that were involved in CLEXI in Australia. Many of the same partners. The one thing that is different is that this center explicitly has industry and government partners that have signed up. If you want another fun anecdote, so we were told that we were funded in November 2022. We opened our doors on the 1st of February 2024. What happened in between? Christian went to sleep. He was just lazy, couldn't be bothered. All that money was lying around. What happened in between? Lawyers happened in between. We have 24 partners in the center. They have to all sign up to a common agreement. It takes 1.5 years to make that happen. Okay? Just so you know who rules the world. It's not scientists, it's not politicians, it's lawyers. So that's how long it took. And so we have 8 industry and government partners. Some of them you might recognize. So in the government space, it's the Victorian government, the federal government, and the New South Wales government through their environment departments mostly. We have this company. Anybody know the logo? Energy Australia. It's an electricity energy company. Deloitte, one of those not so much in a good light at the moment, one of those consultancy companies. IAG is an insurance company. Water New South Wales is what it says. It's a water company. And GSES stands for Global Sustainable Energy Solutions. It's a solar power company, but it's more in a sort of, they think more of deployment. They don't actually deploy, right? So there's more a planning company. And what we want to do with them is really integrate them through what we call a partner integration program in our work, and that goes through designing our research, training. So if you're a student in the new center, we'll probably ask you whether you wouldn't be interested in going to one of these companies or another to have an industry internship. And if you say no, we may say that that's not an option, but that's... we also want to learn from each other and give each other advice. We have a big training program. Melissa has signed up for yet another gig as the graduate director, and we are delighted that she has. Yay! And it's very similar to what you have experienced, except that there's a new component around industry engagement, because we really want you to have that opportunity, and we really want people from industry to come to us as well and spend a few weeks or months with us to get our experience more directly to them. We have a big engagement program, Angela, as you would expect. And it's really, engagement, you have to ask who are you engaging with, and there's a few examples who we want to engage with, right? First, we want to engage with our peers, with other scientists around the world. And of course, the strategy to do that is different from the strategy to engage with governments, for example. So this is all about bringing our research partners on board, having seminars and other ways. We want to engage with the public. There's many familiar things. One of the things we challenged ourselves and still don't know whether we are crazy or whether it's a good idea or we're absolutely crazy is we want to have a podcast. We might ask some of the students to be on it and, have a monthly podcast. No one might listen to it, but then we would be just like most other podcasts, right? No one's actually listening to. We want to engage with the next generation, so we have a program that we started with a charity you may know called Deadly Science, who provide resources for science to indigenous school communities, often rural communities, and we've already deployed through some fortuitous luck, with Deadly Science, we've already deployed about 20 weather stations in schools in indigenous schools. We haven't done anything with them yet, but we've only started on 1st of February. And we want to engage with government by being involved in lots of government processes, just like CLEX is. Think about submissions to government initiatives. All right, so let me summarize why this is such a big challenge and why it's going to be so much fun. So we want to start exactly from the other way. Instead of going to ask climate scientists and say, what would you like to work on? Let me find money for that. Let's get money for what you would like to work on. We start the other way around. We say people have to make decisions around climate change, right? But these decisions are almost always local or regional. Think about, and they can be national, but it's still a network. So think about the renewable energy distribution of assets in the renewable energy grid, right? This anti-correlation, and we haven't even talked about clouds yet, and then we have to talk about clouds and wind together. Clouds are the number one for solar, right? That's where most of the variability comes from. On a cloudy day, you don't make much solar power. On a sunny day, you do. There's also this nasty thing called seasonal cycle that obviously affects things. So in winter, you don't make as much as in summer. But most of these decisions are local. And even if we think about networks, it's networks of local, right? Well, and we've convinced ourselves that what people really care about and what affects these decisions is the local weather. And with weather here, we mean rainfall, wind, temperature on the ground. But then I convinced you that that weather is actually made by weather systems, right? So to do this, we actually really need to understand how weather systems make this. And then we know that these weather systems are embedded in climate variability, right? El Niño, La Niña will change the occurrence and strength of these weather systems. And then all this is sitting on a world that's changing globally. So this is a truly, truly grand challenge. We really need to connect this to this, and across it sit all these things that I've described. But perhaps the innovation that we want to bring in our center is to really, as we think about how this affects this and how this affects this, we want to go and look at it through the lens of how the weather is changing. So yeah, how does the weather change as the climate's changing is the big question. And we've assembled a team. It's bigger than this by now, but I haven't been able to get people's photographs on there and update them. So this is mostly chief investigators, but also our operations team. You see a few people here whose faces you will recognize. These are the people that are signed up at this point. And with that, thank you very much.
Do we have questions for Christian?
Thanks, Christian. I just got a question about the high resolution modeling component. It's a pretty grand plan to get down to such low resolution, but how do we know when we've gotten low enough? Will we get to the end of this program and go, oh, actually we need to get down to the 50-meter scale, or what sets the boundary at 100 meters program?
So there is no boundary. These are estimates. These are guesses. As with all models, it's not about whether they're right or wrong. It's whether they're fit for purpose. And that's a really important thing to realize. You're not asking, is the model right or wrong? You're asking, can I use it for the purpose I want to use it? So if the purpose of our center is to look at scale interactions. And if it's the scale interactions between global and continental, then you may or may not need a 300-meter model to do that. If it's the scale interactions between the turbulence scale or the mesoscales and weather systems, you need very high resolution, but you may not need global. So for us, it's really, we want to go down to higher and higher resolutions and see what can we learn from these higher resolution models that we couldn't learn from the previous ones for the problems we want to look at, which are problems of scale interaction, really. And the limit is, in one sense, computing, but if that was the only limit, that's not a good idea to think of it just as a compute problem, because then A, you would never go to 1 kilometer now because the computing is not good enough. But also, if you've got a big computer, you just do it for doing its sake. And that's also not good. So we really want to keep this fit for purpose in mind. And the purpose is set by the scientists, right? What do you want to do? What do you want to understand? And I would argue you cannot understand the interactions between mesoscale and weather scales with a 100-kilometer model. It doesn't have mesoscales. And if you want to bring the convective scale in and say, I want to understand what the convective scale does to the weather scale, well, now you need to go even higher, right? So it's really what is the question that will set what resolution you need.
I'll go Camille.
Thank you so much. That was really interesting. I'm curious, your center, or the center, aligns perfectly with
Yeah.
energy and weather resources, affordable clean energy as part of the UN SDGs. Is there any interconnections?
It's a really good one. We haven't mapped our activities on those, on the sustainability goals at all yet. That's a really good point. We haven't thought about that. The short answer is we haven't thought about that. We've mostly thought about what might an energy company want to know, or what might an insurance company want to know, or what might the government want to know. We haven't really gone and said, oh, how does what we do map onto? And it's a bit unpredictable as well, because whilst we have these sort of grand, the big picture in place, the smalls, the details will depend, A, on what our industry and government partners come up with in form of questions and ideas. We have had some interactions with them, but it's early days. And it also depends on who you are, right? Who are the people who come in and work with us, because you'll come with your own interests. And that's true for the students, that's true for the postdocs. So while we have this big sort of envelope in which we want to operate, the details, the beauty, the flowers on the tree will come from you, not from us. We just make the tree, we just make the branches. And then making it great will come from you.
Thanks, Christian. Really refreshing to hear more granular sort of description of the climate studies in Australia. Probably a larger discussion, but how do you think the experience of students will be different in 21st century centre?
I should pass that straight on to Melissa. I think it will be great.
Yeah.
I think it will be somewhat different. We're trying to sort of maybe keep the cohort a little smaller at the core and have a large cohort as we have now, but have a core cohort who then can access these industry placements and so on and so forth. So that industry placement will be interesting. The other thing we're trying to do is do much more team-based research, as in larger teams working together. So as a student, your main meeting will be not just with your supervisor or supervisors, but it will be interspersed with meetings with the entire team that, say, works on climate variability and weather system change.